I think most people, myself included until I read this, imagine the lungs are these big bags just sort of glued to the inside of your ribs. Like, you
Hmm.
pull your ribs out and the lungs are stuck to them so they stretch. But that is not true, is it?
Not at all. And this is the first major concept we really need to get our head around. The floating lung.
Okay, the floating lung.
Anatomically, the lung is literally floating inside the thoracic cavity.
Floating in what? Like in air? Water?
Well, it's floating in the thoracic cavity, but it's surrounded by a very, very thin layer of what's called pleural fluid.
Pleural fluid.
Right. Think of the chest cage. You've got the ribs, the sternum, the vertebrae as a rigid box.
Okay.
Inside that box, you have the lungs. But here is the key detail, and it's a wild one. There are no physical attachments between the lung tissue itself and the chest wall. None.
Wait, pause for a second. You're telling me my lungs, these vital organs keeping me alive, aren't actually attached to my chest?
Well, except for one spot right in the center where all the pipes come in. The airway, the blood vessels. That's called the hilum.
The hilum.
Aside from that one anchor point, they are completely unattached.
That sounds precarious. I mean, if I jump up and down on a trampoline, why don't they just, slap against the bottom of my rib cage? That sounds like a design flaw.
It would be a massive design flaw, if not for the physics of that pleural fluid we just mentioned. This is where the engineering gets absolutely brilliant. It acts as both a lubricant and a glue.
How could it be both? I mean, lubricant makes things slip, glue makes things stick. That seems like a contradiction.
Okay, think about this. Imagine you have two glass slides, like what you'd use under a microscope.
Yep.
You put a single tiny drop of water between them and press them together. Now, you can slide them back and forth against each other incredibly easily, right? Almost no friction.
Yeah, they're super slippery. Almost frictionless.
Extremely slippery. That's the lubricant function of the pleural fluid. It lets the lungs slide smoothly up and down against the chest wall as you breathe.
Okay, that part makes sense.
But now, try to pull those two glass slides apart, just straight outward. Try to separate them.
You can't. They stick. The water holds them together like glue.
Exactly. The surface tension of that fluid creates this massive suction force. It holds the lungs open right up against the chest wall. So the lung floats, it slides, but it is pinned to the wall by fluid dynamics.
So my lungs are basically suction cupped to the inside of my ribs.
Effectively, yes. That's a great way to put it.
That is a really cool image. Okay, so we have this slippery, sticky, floating lung. Now we have to actually move air into it. The source material talks about two main ways we expand the lungs. One is the up and down method, and the other is the front and back method.
That's a good way to simplify it. Let's start with the first method, which is really the heavy lifter for normal, quiet breathing, and that's the diaphragm.
The muscle everyone tells you to sing from.
The very same. The diaphragm is this big dome-shaped muscle that sits right under your lungs. It's the floor of your chest cavity, and it acts like a piston.
A piston?
During inspiration, that's breathing in, the diaphragm contracts and it pulls downward. Because it pulls down, it lengthens the chest cavity, it creates more vertical space.
And because the lungs are suction cupped to the wall in the diaphragm, when the floor drops out, the lungs have to stretch down with it.
Correct. That downward pull stretches the lungs, which lowers the pressure inside, and that pulls air in. Now, here is the really interesting part about expiration, or breathing out.
Okay.
In normal, quiet breathing, you don't actually use any muscles to breathe out.
Wait, really? It's completely passive?
Entirely passive. I mean, think about it. You spend energy to stretch a rubber band, right?
Sure.
But do you spend energy to let it go?
No, it just snaps back on its own.
Exactly. When you breathe out, the diaphragm just stops contracting, it relaxes, and then the elastic recoil of the lungs, remember they want to collapse, and the weight of the chest wall just sort of gently squeezes the air out. It's like letting go of that stretched rubber band.
So breathing in is work, but breathing out is just letting go. That's actually kind of poetic.
At rest, yes.
Yeah.
But what if you are breathing heavily? Say you're running for a bus or doing high-intensity interval training.
Right. I'm definitely not letting go then. I'm forcing the air out.
You are, because in that case, elastic recoil isn't fast enough. You need to force the air out quickly. And that's when you recruit the abdominal muscles.
The abs, the six-pack.
The abdominal recti specifically. They contract and they push the abdominal contents, your stomach, your liver, your intestines upward. That shoves the diaphragm up into the chest cavity like a powerful piston, forcing air out rapidly. It turns that passive process into a very active pump.
Okay, so that's the up and down piston motion. But I also feel my chest getting bigger outwards when I take a huge breath. If I put my hands on my ribs, they're definitely moving.
That is the second method, elevation of the rib cage. And this is all about leverage.
Leverage, okay.
In a resting position, your ribs aren't horizontal. They slant downward toward the front.
Sort of like the slats of a blind that are partly closed.
That's a good analogy. Or think of a bucket handle hanging down against the side of a bucket.
Right, okay.
When you lift that handle, it doesn't just go up. It moves up and out, away from the bucket.
Oh, I see. So lifting the ribs pushes them away from the spine.
Exactly. When you contract the muscles to lift the ribs, they project forward. The sternum, your breastbone, moves forward, away from the spine. This increases the anteroposterior diameter, which is just the thickness of your chest from front to back.
The text mentioned a percentage here, and it was surprisingly large.
Yes. It increases that front-to-back dimension by about 20% during maximal inspiration. That is a massive volume increase.
So we have the diaphragm pulling down, creating vertical space, and the ribs lifting up and out, creating horizontal space. It's a 3D expansion.
It is a very efficient one.
So let's talk about the teams of muscles involved here, because the source breaks them down into muscles of inspiration and muscles of expiration. It's like a biological tug of war.
It really is. The lifters, or the muscles of inspiration, are led by the external intercostals. These are the muscles running between your ribs. They're the main players in lifting the rib cage.
External intercostals, got it.
But you also have accessory muscles for when you're breathing really hard. The sternocleidomastoid, that big muscle in your neck that you can feel when you turn your head.
Okay.
That lifts the sternum up. Then you have the anterior serrati, which lift many of the ribs, and the scaleni, which lift the first two ribs specifically.
So it's a whole crew lifting the cage from different angles.
Exactly. And on the opposing team, the pullers, or the muscles of expiration, we already mentioned the abdominal recti pulling down on the lower ribs.
Right, for forced expiration.
But you also have the internal intercostals.
Okay, hold on. We have external intercostals and internal intercostals. That sounds confusingly similar. And they do opposite things. How does that even work?
This is a beautiful piece of geometry, actually. If you look at figure 38:1 in the source material, it shows the leverage perfectly. The external intercostals slant forward and downward, from one rib to the one below it.
Okay, and I'm picturing that.
When they contract, because of that angle, they pull the lower rib up and forward towards the upper rib. That's inspiration. They're lifting.
Right.
But the internal intercostals slant in the opposite direction, backward and downward. So when they contract, they pull the upper rib down towards the lower rib. It's a perfect antagonistic system.
So one set opens the blinds, and the other set shuts them, just based on the angle they're pulling from.
Precisely. It's all in the geometry of the fibers.
That is incredible engineering. Okay, so we've got the pump mechanics down. But a pump is useless without pressure differences. This is where we get into the physics of it all. And frankly, this part confused me a little at first, so walk me through it. We have these different types of pressures: pleural, alveolar, and transpulmonary. Let's start with pleural pressure.
Right. Remember that fluid we talked about, the one between the lung and the chest wall?
The sticky lubricant stuff.
Exactly. Pleural pressure is the pressure of that fluid. And the most critical thing to understand is that it is negative pressure.
Negative pressure means suction, right? Like a vacuum.
Precisely. It's a slight suction. At the start of a normal breath, before you even inhale, that pressure is about -5 centimeters of water. We use centimeters of water because the pressures are so small.
Yeah.
So -5 centimeters H2O.
Okay, so there's a constant vacuum holding my lungs open. Why -5? Why not 0?
That's the key question. It's because the lungs are always trying to do one thing and the chest wall is trying to do another. The lung tissue, with its elastic fibers, is constantly trying to recoil and shrink to collapse.
Okay.
But the chest wall has its own natural tendency to spring slightly outward, so they are constantly pulling away from each other in that little space. That Medicare 5 is the measurement of that tension. If it were 0, the lungs' recoil would win and it would collapse.
So Medica 5 is the baseline tension that keeps the system stable at rest.
Exactly. Then, during inspiration, you expand the chest cage. You actively pull the walls away. This creates more suction in that space. The pressure drops to about -of 7.5 centimeter H2O.
So you're increasing the vacuum.
You are. And that extra suction pulls the lung surface outward, expanding the lung volume.
So the chest wall moves first, creates a bigger vacuum, and the lung gets dragged along for the ride.
That's a perfect description. Now let's look inside the lung. That's alveolar pressure. This is the pressure of the air inside the alveoli, the tiny air sacs.
Yep.
When your glottis, your throat is open and no air is moving, the pressure inside your lungs is equal to the atmospheric pressure outside. We call this our 0 reference point, so 0 centimeters H2O.
Okay, so 0 just means the same pressure as the room I'm sitting in.
Right. Now, to get air to flow in, physics dictates you need the pressure inside to be lower than the pressure outside. Air always flows from high pressure to low pressure.
Makes sense.
So during that 2-second inspiration, the alveolar pressure drops just slightly below zero to about -1 centimeter H2O.
That doesn't sound like much. -1. Is that all it takes?
It's tiny. But that slight vacuum, that tiny pressure difference, is enough to pull in about 0.5 liters of air, your normal tidal volume.
Wow, that's incredibly efficient.
And then for expiration, it's just the reverse. The elastic recoil compresses the lungs, the pressure inside rises to about +1 centimeter H2O, and that's enough to gently push that 0.5 liters of air back out.
Okay, so we have pleural pressure, the outside suction, and alveolar pressure, the inside air. With this third one, transpulmonary pressure.
This is simply the difference between the two we just discussed. It's the difference between the pressure inside the alveoli and the pressure on the outside surface of the lungs in that pleural space.
Why does that specific number matter? What does it tell us?
It's the most important one, in a way. It measures the recoil pressure. It is a direct measure of the elastic forces in the lungs that are trying to collapse them at any given moment. It's basically a measurement of the tension in the balloon wall. The higher the transpulmonary pressure, the more the lung is stretched.
Ah, so it's the real stress on the lung tissue itself.
Exactly.
Speaking of tension in balloons, that brings us perfectly to section 3. Compliance. Now, compliance is one of those words that means something totally different in, say, an HR department than it does in physiology.
Very different.
When we talk about lung compliance, what are we actually measuring? Is it stiffness? Stretchiness?
Think of it as distensibility.
Yeah.
Or simply stretchiness. Let's go back to the balloon analogy. Imagine you have a balloon made of thick, heavy rubber and another balloon made of thin, flimsy latex.
Okay.
If you blow into both of them with the exact same amount of force, let's say 1 centimeter of water pressure, the flimsy balloon is going to inflate a lot. It's very distensible. It has high compliance. The thick rubber balloon might barely move. It resists stretching. It has low compliance.
So high compliance is actually good in this context. It means the lung is easy to inflate.
For the most part, yes. A healthy lung is very compliant. In a normal adult, for every 1 centimeter of water pressure we apply, the lungs should expand and accept 200 milliliters of air. That's the benchmark number.
And if that number drops?
If that number drops, say in a disease like pulmonary fibrosis, where the lungs become stiff and scarred, your compliance goes way down. Your lungs become like that thick rubber balloon. Your respiratory muscles have to work 5-10 times harder just to get the same amount of air in. It's exhausting.
Is that a straight line relationship? Like you pull a little, you get a little, you pull a lot, you get a lot?
Interestingly, no. And this is shown in the compliance diagram in the source, figure 38-12. The curve for inspiration follows a different path than the curve for expiration. We call this hysteresis. But the key thing to understand is why the lung resists expansion in the first place. What are those forces?
Right. What are we actually fighting against with every breath?
The source defines 2 types of elastic forces causing this recoil. The first one is what you'd probably expect. It's the tissue elasticity itself, the actual elastin and collagen fibers woven throughout the lung parenchyma.
The actual fabric of the lung.
Right. Think of a nylon stocking or a web of rubber bands. When the lung is deflated, those fibers are contracted, they're kinked, they're folded. When you expand the lung, you stretch and unkink them. That accounts for about 1/3 of the lung's total elasticity.
Only 1/3. I would have guessed the tissue itself is the main thing stretching.
That's the big surprise. 2/3 of the elastic tendency to collapse comes from something else entirely. Surface tension.
Surface tension again. We talked about it with the pleural fluid holding the lung to the chest wall.
Yeah.
This is happening inside the lung.
Yes, inside every single one of the 300 million alveoli. This was proven by a really fascinating experiment described in the source, in figure 38-4. They compared the compliance of lungs filled with air versus lungs filled with a saline solution.
Saline.
Yeah.
Like salt water. So they basically drowned the lung for the experiment.
Effectively, yes. They took a lung, removed it from the body, and filled it with fluid.
I would assume a lung full of water is much harder to inflate than a lung full of air. Water is heavy.
That's the intuitive thought, but the result was the exact opposite. When the lung is filled with saline, there is no air-fluid interface. There's no surface. It's just fluid against fluid-wetted tissue, so there's no surface tension.
And what happened to the compliance?
The lung became incredibly easy to expand. It was floppy. It required only about 1/3 of the pressure to inflate compared to the normal air-filled lung.
Wow, so all that effort, all that stiffness, It's not the lung tissue, it's the air itself, or rather, the air meeting the wet surface of the lung.
Precisely. That air-fluid interface creates a massive elastic force that is constantly trying to collapse the lung. And this leads us to what is arguably one of the most miraculous substances in the entire human body, surfactant.
Section 4. The miracle of surfactant. I know this is a huge deal for premature babies, but explain the chemistry here. Why does a thin layer of water want to collapse my lungs so badly?
It all comes down to the properties of water. Let's use the raindrop analogy from the source. Water molecules have a very strong attraction to one another. They're polar molecules. They want to stick together. In a raindrop, the water molecules on the surface pull together as tightly as possible, trying to form the smallest possible shape for a given volume, which is a sphere. They're literally squeezing the drop into a ball.
Okay, they like to huddle up.
Now, reverse that. Imagine the inner surface of an alveolus, one of those tiny air sacs, is lined with a thin film of water. Those water molecules are attracted to each other. They want to pull together. This creates a force that tries to contract the alveolus to shrink its surface area, forcing the air out and causing the sac to collapse.
So every single one of my millions of alveoli is trying to shrink into a tiny dot because of the water lining them.
Yes, and if that surface tension were that of pure water, which is about 72 dynes per centimeter, your lungs would likely collapse. Or you would need such incredible muscular effort to keep them open that you would become exhausted just from breathing.
But our lungs don't collapse. So enter surfactant, the hero of the story.
Exactly. Surfactant is this complex mixture. It's mostly phospholipids, but also proteins and ions, and it's secreted by special cells in the lungs called type 2 alveolar epithelial cells.
Okay.
These cells only make up about 10% of the surface area of the alveolar, but their secretion is absolutely vital for life.
So what does it do? How does it fight the water?
It acts like a detergent. The surfactant molecules have a part that dissolves in water and a part that doesn't. So they spread out over the surface of the fluid lining the alveoli. They essentially get in between the water molecules and break up that strong attraction they have for each other. They reduce the surface tension drastically.
Give me the numbers. How much is a difference are we talking about here?
It's a huge difference. Pure water, as we said, is 72 dynes per centimeter. The normal fluid in the lungs without surfactant would be about 50. But with surfactant, it drops that surface tension to somewhere between 5 and 30 dynes per centimeter.
That is enormous. That's like a 5 to 10-fold reduction in the force that's trying to collapse the lung.
It is massive. And there is a physics principle here called the law of Laplace that makes this even more critical and even more clever.
Okay, the law of Laplace.
The formula is pressure equals 2 times the surface tension divided by the radius of the alveolus.
Okay, we promise no heavy math, but divided by radius is the key part. That means the size of the bubble matters. A lot.
It means everything. Think about a fraction. If the bottom number, the radius, is very small, the resulting pressure is very high.
Which is a huge problem because the lungs are made of millions of tiny alveoli, not a few big ones.
Exactly. The smaller the bubble, or the alveolus, the higher the collapsing pressure generated by surface tension. Without surfactant, the small alveoli would have a much higher collapsing pressure than the large ones. They would collapse instantly, forcing their air into the larger, more stable alveoli. The lung would become incredibly unstable, like a bunch of interconnected soap bubbles of different sizes.
And this is the exact issue with premature babies, right?
Yes, this is the cause of what's called respiratory distress syndrome. Surfactant doesn't begin to be secreted in significant amounts until the 6th or 7th month of gestation. If a baby is born before that, their lungs have a surface tension that's closer to pure water, 6 to 8 times the normal adult tension.
So they are fighting a losing battle against physics with every single breath they take.
It's a heartbreakingly difficult battle against physics. Their tiny alveoli have an extreme tendency to collapse. Before modern medicine introduced surfactant replacement therapy and positive pressure breathing machines, this was often fatal simply because the work of breathing was too great. They would essentially suffocate from exhaustion.
It's incredible to think that this one chemical is the difference between life and death.
It truly is.
Speaking of the work of breathing, let's move to Section 5. We've established that breathing takes energy, but the source makes a very clear distinction between the compliance of the lung by itself and the compliance of the whole system.
Right. We've been talking about how stretchy the lung tissue is, but the lung doesn't exist in a vacuum. It's inside a cage. And the rib cage and the muscles have their own resistance. They're heavy, they have friction, they have their own elasticity.
Right.
So when you measure the compliance of the entire system, the lungs plus the chest cage, it's about half that of the lungs alone.
So the chest cage stiffens the whole operation significantly.
Yes. Instead of that 200 milliliter per centimeter of water pressure for the lungs alone, the combined system is about 110 milliliters. And interestingly, the chest cage becomes very stiff at very high volumes or very low volumes. It has a sweet spot in the middle range where it moves most easily.
Okay, so the work we do has to overcome the lungs in the cage. The force lists 3 specific types of work that consume energy during breathing. Let's break them down.
Sure. First, you have compliance work or elastic work. That's what we've been discussing. The work required to expand the elastic forces of the lung and the chest. That's the majority of the work in normal breathing.
So, fighting that recoil.
Second is tissue resistance work. This is the energy you spend overcoming the viscosity of the structures. As the lungs and chest walls slide against each other, and as tissues deform, there is internal friction.
Like trying to move a rusty hinge, but on a microscopic level.
A little bit, yes. And third is airway resistance work. This is the energy required to physically push the air molecules through the trachea and the bronchial tree. There's friction between the air and the walls of the tubes.
The friction of the air itself.
Correct. Now, normally, quiet breathing is incredibly efficient. It only consumes about 3% to 5% of your total body energy expenditure.
That's incredibly cheap considering it keeps us alive.
It is, but, and this is a big good, but during heavy exercise, that energy cost can jump 50-fold.
50 times? That seems almost impossible. How could it increase that much?
Think about the velocity of the air. You are moving massive amounts of air very, very quickly. And friction increases exponentially with velocity. The respiratory muscles start working so hard that they become a major consumer of oxygen and energy themselves. In fact, this is a major limiting factor in elite athletic performance.
What do you mean by a limiting factor? I always thought it was the heart or the leg muscles that gave out.
They do, but the respiratory muscles can be the bottleneck. Eventually, you reach a point where your body cannot provide enough additional oxygen to support the breathing muscles and the running muscles. The bellows cost too much to run. You aren't stopping because your legs are tired. You're stopping because it costs too much energy simply to get the air in to feed the legs.
That is a wild thought. A biological ceiling imposed by the cost of breathing.
Exactly.
Okay, let's get practical. How do doctors actually measure all of this? We see these charts in the source material with waves going up and down. This is section 6, spirometry.
Spirometry is the classic method for recording lung volume changes. The setup described in the text is old school, but illustrates the principle perfectly. Imagine a drum floating inverted over a chamber of water with the air chamber connected to a breathing tube.
Okay.
As you breathe in and out of the tube, the drum rises and falls. A pen attached to the drum records that wiggle on a moving sheet of paper.
Very analog.
Very, but very effective. And it allows us to define 4 specific lung volumes. These are the fundamental building blocks of lung capacity.
Let's run through them. First is the tidal volume.
That's your normal quiet breath, the in and out you're doing right now. It's about 500 milliliters for a healthy adult man, just a small fraction of your total capacity.
Okay. Next up is the inspiratory reserve volume.
This is the extra gas in the tank. Take a normal breath in. Now, at the end of that normal breath, keep inhaling. Suck in as much air as you physically can until you can't take in anymore. That extra amount above and beyond the normal breath is the inspiratory reserve, and it's huge, about 3,000 milliliters.
So we have this massive backup tank we don't normally use.
Exactly. Then there's its opposite, the expiratory reserve volume. Breathe out normally. Now, at the end of that normal exhale, force every last bit of air out of your lungs you possibly can. Squeeze it all out. That extra 1,100 milliliters or so is the expiratory reserve.
And finally, the one that causes all the problems for measurement, the residual volume.
Right. This is the air that you cannot exhale no matter how hard you try. If you force it all out, the lungs would go completely flat and the airways would collapse. There's always about 1,200 milliliters of air left behind.
But wait, if I can't breathe it out, the spirometer drone can't measure it, right? Because nothing is moving into or out of the machine.
You've hit on the central problem of spirometry. It can only measure the air that moves. It cannot measure the residual volume directly.
So how on earth do doctors measure it? If it's trapped inside me, how do you know how much is there?
It's a great logic puzzle. To find the residual volume, you have to measure it indirectly. The classic way is with a trick, the helium dilution method.
Helium dilution, how does that work?
Okay, imagine you have a swimming pool, but you don't know how big it is. You can't measure it with a tape measure. But you have a small bucket of very concentrated red dye. You know exactly how much red dye you have.
So I pour the dye into the pool.
You pour it in, wait for it to mix perfectly, and then you take a cup of water out and measure how red it is. If the water is essentially clear, you know the pool is massive. If the water is bright red...
The pool is pretty small.
Exactly. We do the same thing with helium. We have the patient breathe from a spirometer of a known size that contains a known concentration of helium. Helium is used because it doesn't cross over into the blood, it just stays in the lungs. You let the patient breathe until the helium in the spirometer mixes completely with all the air in their lungs, including that hidden residual air.
Then you just measure how much the helium got diluted.
Yeah, precisely. From the final concentration, you can calculate the total volume of air the helium mixed with. That gives you what's called the functional residual capacity. From there, you can subtract the parts you already know, like the expiratory reserve, to find the hidden residual volume.
That is incredibly clever. Now, when we add these volumes together in different combinations, we get capacities. The big one everyone talks about is vital capacity.
Vital capacity is a crucial measurement. It's the...
Okay, so we're moving all this air. But the goal isn't just to move air, it's to get fresh air to the blood for gas exchange. And this brings us to Section 7, ventilation versus dead space. This is a concept I found fascinating. Not all the air you breathe in actually counts.
That's exactly right, and it's a critical concept. Think about your anatomy. You breathe in through your nose, the air goes down your pharynx, your throat, then your larynx, your trachea, your bronchi. These are just tubes. They are conducting passageways.
Right, they're pipes.
Gas exchange oxygen entering the blood and CO2 leaving only happens way down at the end of the line in the alveoli.
So the air that's just sitting in my nose and throat is... what? Is it just waiting?
It's wasted from a gas exchange perspective. We call this volume of air in the conducting airways the anatomical dead space. In a typical adult, it's about 150 milliliters.
That's a pretty significant amount. That's almost a third of a normal breath.
It is. Every time you take a 500 milliliter breath, the first 150 milliliter of new air just goes to fill these tubes and never reaches the blood. It just pushes the old, stale air from the last breath down into the alveoli. And then the first 150 milliliter you breathe out is just that fresh air from the tubes that never got used.
It's like breathing through a really long snorkel.
Yeah.
The air that's stuck in the snorkel just goes back and forth. It never gets exchanged.
That's the perfect analogy, and that's why rapid, shallow breathing is so inefficient. If you take tiny 200 milliliter breaths, but your dead space is 150 milliliters, you're only actually getting 50 milliliters of fresh air to your lungs with each breath. You are basically suffocating yourself while panting.
Now, the source makes a distinction between anatomical dead space and physiological dead space. What's the difference?
Anatomical dead space is just the physical volume of the tubes. Physiological dead space includes the anatomical dead space plus any alveoli that aren't working properly.
Broken alveoli.
Right. For whatever reason, maybe they have poor blood flow or maybe the alveolar walls are damaged. So even though air is getting to them, no gas exchange is happening. They are also functionally dead space.
So in a perfectly healthy person.
In a healthy person, these two numbers are nearly identical because basically all our alveoli are working. But in someone with lung disease, like emphysema, the physiological dead space can be huge. They might be breathing, but half their lung isn't doing any gas exchange.
So the metric that really matters isn't just how much air am I moving per minute, but something called alveolar ventilation.
Correct. Alveolar ventilation is the true measure of how much new air is actually reaching the gas exchange surfaces each minute. The formula is simple. It's your respiratory rate multiplied by your tidal volume minus your dead space volume. That's the number that really counts for keeping you alive.
It really emphasizes the quality of the breath over just the sheer quantity.
Absolutely.
Let's move to the pipes themselves. Section 8, the airways. We have the trachea, bronchi, bronchioles. It's this massive branching tree. But the structure changes significantly as you go deeper.
It does. The trachea and the larger bronchi need to be held open at all times so they don't collapse when you suck air in. So they have extensive cartilage rings, or in the bronchi, curved cartilage plates. It's like the hose of a vacuum cleaner. It's reinforced to prevent it from kinking.
But deeper down in the smallest tubes, the bronchioles, that cartilage disappears.
Yes. The bronchioles are almost entirely smooth muscle. They don't have cartilage. They are kept open not by their own rigidity, but by the same transpulmonary pressures that expand the alveoli. They are tethered to the surrounding lung tissue. As the lung expands, it pulls the bronchioles open.
Now, my intuition would tell me that the tiniest tubes, the termobronchioles, would offer the most resistance to airflow because they're so small. It's like trying to drink a thick milkshake through a coffee stirrer.
That's a very common misconception, and a very logical one. But it's actually the medium-sized bronchi that have the greatest resistance.
Why? That just defies logic.
Because while the individual bronchioles are tiny, there are millions of them arranged in parallel. The total cross-sectional area of all the bronchioles combined is massive, far greater than the area of the trachea. So the air, once it gets down there, is flowing through them very slowly and with very little resistance. The real bottleneck is actually higher up in the median branches before the airway has branched out so extensively.
That is genuinely surprising. But the bronchioles are still vulnerable, aren't they?
Yeah.
Because they don't have cartilage.
Very. Because they are all muscle, they can clamp shut. And this is precisely what happens in an asthma attack. The smooth muscle goes into spasm and constricts, occluding the airway. Mucus and edema can also easily block these small airways.
And this is all controlled by the nervous system. We have the sympathetic and parasympathetic systems fighting for control of the airway size.
Right. Think fight or flight for the sympathetic system. If you are running from a tiger, you need as much air as possible. So the sympathetic system, and specifically circulating hormones like epinephrine and norepinephrine from the adrenal gland cause bronchodilation, they relax the smooth muscle and open the airways wide.
Which is why an EpiPen or a rescue inhaler works for an asthma attack. It's mimicking that open up signal.
Exactly. Most inhalers are beta-adrenergic agonists, which is what epinephrine acts on. On the flip side, you have the parasympathetic system, which comes from the vagus nerve. It releases acetylcholine, which causes constriction.
So that's the rest and digest mode.
It is, but it's also a protective reflex. If you inhale smoke, dust, or irritating gases like sulfur dioxide, reflexes are triggered that cause the parasympathetic system to clamp the airways shut to try and keep the bad stuff from getting deeper into the lungs.
Speaking of keeping bad stuff out, what about the cleaning crew? The mucus and the cilia?
A vital and often underappreciated defense mechanism. The entire surface of the respiratory passages is kept moist by a layer of mucus that traps inhaled dust and other particles. But you can't just let that mucus sit there and accumulate.
Right.
The entire surface is also lined with millions of cilia. These are tiny hair-like structures that are constantly in motion.
And they all move in one direction.
They beat continually and in a very specific coordinated direction towards the pharynx. It's called the mucociliary escalator.
I love that name. It's so descriptive.
It's perfect. The cilia in the lower lungs beat upwards, constantly carrying that sheet of mucus up to the throat, where it can be swallowed or coughed out. The cilia in the nose beat downwards, doing the same thing.
So we are constantly, unconsciously swallowing a tiny stream of trapped dust and mucus.
Appetizing, isn't it? But it's what keeps your lungs sterile.
Sometimes, though, the escalator just isn't enough. You need the heavy artillery. Section 9. Reflexes. The cough and the sneeze. The source breaks down the cough into a step-by-step launch sequence that is remarkably violent.
It is a controlled explosion. Let's walk through the cough mechanism.
You take a rapid, deep inspiration, about 2.5 liters of air.
The epiglottis closes over the larynx, and the vocal cords shut tight. You are trapping that air.
The abdominal muscles contract violently, pushing the diaphragm up against the lungs. The pressure inside the lungs spikes to 100 millimeters of mercury or even more.
So you're building a pressure bomb inside your chest. 100 millimeter Hg is like, what, systemic blood pressure level force?
It's a huge amount of pressure. Step 4. The vocal cords and epiglottis suddenly fly open.
The air blasts out. Because the pressure gradient between the lungs and the atmosphere is so high, the air explodes outward at velocities ranging from 75 to 100 miles per hour.
100-mile-per-hour winds inside your throat.
And here's a crucial detail that makes it even more effective. The high positive pressure in the chest actually collapses the non-cartilaginous parts of the trachea and bronchi, forming narrow slits.
Why is that a good thing? It sounds like it's choking you.
Think of putting your thumb over the end of a garden hose. By narrowing the opening, the water shoots out faster and with more force. By narrowing the trachea into slits, the velocity of the air increases dramatically, and it creates a scouring force that blasts out any foreign matter or excess mucus.
That is brilliant design. And the sneeze, is it the same thing?
Very similar mechanics, but the trigger is different. A sneeze is triggered by irritation in the nasal passages, and the afferent signals are carried by the trigeminal nerve. The pressure buildup is the same, but during the explosive release, the uvula depresses.
The little punching bag thing in the back of the throat?
Yes, it drops down, and that directs a large portion of the rapidly moving air through the nose instead of just the mouth. It's specifically designed to clear the nasal passageways.
It's amazing how coordinated and specific that is. Speaking of the nose, let's talk about Section 10. We tend to think of the nose as just a decoration or a smell detector, but the source describes it as a high-tech air conditioning unit.
It is indispensable for lung health. The source points out that if you have to breathe through a tube directly into your trachea, like in a tracheostomy, it can cause serious lung crusting, infection, and damage. The nose performs 3 critical air conditioning functions: warming, humidifying, and filtering.
How efficient is it at those things?
Incredibly efficient. By the time air you breathe in reaches the trachea, it is warmed to within 1 degree of body temperature and humidified to within 2 to 3% of full saturation.
Even if I'm in the Arctic, breathing freezing, dry air.
Yes. The nose has this extensive surface area because of the conchae, or turbinates, and the septum. It creates this large, warm, wet surface that conditions the air almost instantly as it passes over. If this didn't happen, the cold, dry air would desiccate the lungs.
And filtration.
The hairs in your nostrils catch the big stuff, obviously, but for smaller particles, the nose relies on a process called turbulent precipitation.
Turbulent precipitation. What on earth is that?
It's like drifting a car around a corner. The air, as it flows through the nose, is forced to hit all these obstructions, the conchae, the septum, and change direction rapidly. The air can make the turn, but the particles, having more inertia, can't. They crash into the mucus-coated walls and get trapped.
So the heavy stuff slams into the wall because it can't take the corner fast enough.
Exactly. It's a very effective, non-biological filter.
Let's touch briefly on the voice. The source lists phonation and articulation as the 2 main mechanics.
Right. Phonation happens in the larynx, which is your voice box. The vocal cords act as vibrators. The sound is generated by them vibrating as air passes through. By stretching them or changing their shape using the thyroid and amitinoid cartilages, you change the pitch.
Like tightening or loosening a guitar string.
A perfect analogy. And then articulation is how we shape that raw sound into words using our lips, tongue, and soft palate. But don't forget the third component, resonance. The mouth, the nose, the sinuses, even the chest cavity act as resonating chambers that amplify and add quality to the sound.
Which is why you sound so different when you have a cold up. Your nasal resonators are all blocked up.
Your resonance changes entirely.
We're nearly at the end of our journey here, but we have to mention the blood. We've done all this work to get the air in. Now the blood needs to show up and pick up the oxygen. Section 11 covers a snippet from Chapter 39, Pulmonary Circulation.
And the key takeaway here is that the lungs actually have 2 separate circulatory systems doing 2 different jobs.
Okay.
One is the high-pressure, low-flow system. This is systemic arterial blood coming right off the aorta that feeds the tissues of the trachea and bronchial tree themselves. It brings oxygen to keep the lung structures alive.
So that's the maintenance crew supply line.
Right. The second, much larger system is the low-pressure, high-flow system. This is the pulmonary artery coming from the right ventricle of the heart. It brings the entire cardiac output of deoxygenated venous blood to the alveoli specifically for gas exchange.
And the pressure in that system is much lower than the rest of the body.
Much, much lower. The right ventricle only has to pump blood next door to the lungs, so its pressure is only about 25 millimeters of mercury systolic compared to the left ventricle's 120. The pulmonary vessels are very thin, very distensible, and very compliant. This low-pressure system can easily accommodate the entire stroke volume of the heart.
And the text mentions the lungs also act as a blood reservoir.
They do. The lungs hold about 450 milliliters of blood at any given time. That's about 9% of your total blood volume, and that volume can change. If you have a hemorrhage and lose blood elsewhere, the pulmonary circulation can constrict and shift some of that blood into the systemic circulation to help maintain your blood pressure.
One last technical point the source mentions: wedge pressure. This sounded like something a spy would use. What is it, and why do doctors measure it?
It's a very clever diagnostic trick. Doctors often need to know the pressure in the left atrium of the heart, as it's a key indicator of things like congestive heart failure. But you can't easily stick a pressure catheter into the left atrium. It's deep in the chest and on the high-pressure side of the heart.
So what do they do instead?
They float a catheter through the veins, through the right side of the heart, into the pulmonary artery, and then they guide it out into a small branch until it wedges tight and can't go any farther. This blocks the blood flow in that tiny branch.
Okay, so it's a temporary tiny clog.
Exactly. And because the flow is stopped, the pressure measured at the tip of that catheter is no longer seeing the pulmonary artery pressure. Instead, it's looking downstream through the capillaries, and it essentially reflects the pressure in the pulmonary veins and ultimately the left atrium.
It's like stopping all the traffic on a side street to see how badly backed up the main bridge is just ahead.
Perfectly put. A normal wedge pressure is low, about 5 millimeter Hg. If it's high, it tells you that pressure is backing up from the left heart, which is a classic sign that the left ventricle is failing to pump blood out effectively.
That is absolutely ingenious,
Yeah.
using the lungs plumbing to spy on the heart.
It shows how interconnected the whole system is.
So let's try and synthesize this whole journey. We started with this idea of a floating lung pinned to our ribs by the suction of a thin fluid layer. We used a diaphragm piston and leveraging ribs to create a tiny vacuum inside.
That vacuum then had to overcome the lung's own desire to collapse, a desire driven mostly by the crushing force of surface tension at the air-water interface inside millions of tiny sacs.
And we fought that force with a chemical miracle called surfactant. We filtered the air, heated it, humidified it, and had systems in place to blast out intruders with 100-mile-per-hour coughs.
Yeah.
And finally, after all that, we brought that perfectly conditioned air to a low-pressure bloodbath for exchange.
When you lay it all out like that, it's a system of truly profound efficiency and elegance. It has to balance structural fragility, the need for membranes to be incredibly thin for gas exchange, with robust defenses. And it manages the energy costs so effectively that we barely notice we are doing it 20,000 times a day.
But, as you said earlier, there is a limit. And that's the thought I want to leave everyone with today. The source mentions that during peak exercise, the respiratory muscles themselves can begin to demand so much energy and so much oxygen that the body literally cannot support both them and your running muscles.
That is the so what for me. We often think our limits are psychological, willpower, or maybe just our heart rate. But the text implies something deeper, that at the very peak of human performance, we are limited by the cost of the air we breathe. The machine that powers us eventually consumes all the power it generates just to keep itself running.
A biological speed limit written into the very physics of our chests. That is where we will leave it for this deep dive. Thanks for breathing along with us.
Keep ventilating, everyone.
See you next time.